vanishes. That is the condition. So space derivative of this vanishes, and that would again make all our boundary terms vanish. Right? So, and then as a result of this, what we are left with, so when you plug in this value and this value right here, here and here, and then you carry out the integrations term by term, you have 4 terms. This term, this term, this term, and this term. And for this term, the one single time derivative, time integration with time alone makes it vanish. Here, this integration over sigma would give me this value. However, and this I would look at the expression for pi mu sigma. In pi mu sigma, I have a x prime free in the numerator. Could you please check? In pi mu sigma, there is a x prime mu in the numerator. There is one x prime mu in the numerator. So when you ask x prime mu to vanish, it would collapse. Okay, it would vanish. So perhaps we don't need to write. So we have these 2 terms simply go away, and then this and this we can sum up again. So I erase some of these things here. And I removed even this term. What was this term? Let me recreate it. X mu, this was del tau, this was pi mu tau, I think so. And this was the total derivative term. So, what I am left with is delta S, this is minus 1 and minus t into d tau into d sigma and 0 to some L, ti to some tf, and times del tau over pi mu tau plus del sigma pi mu sigma times delta x mu. Okay, this delta x mu is there, and then our very simple argument that we always give beginning from classical mechanics to field theory to string theory, that because this delta of S has to vanish, our right hand side also has to vanish, and we remember that this delta x mu is non-zero and is arbitrary, and therefore this guy has to vanish. And this is our equation of motion for the action. Now we go to action. We would like to see, could I write my equation of motion for the Polyakov action in the analogous fashion? Yes, the answer is yes, I could. Let me try to do that. So that's our equation of motion, and let me remove some of these things from here. Then I could remove this, and then this simply equated to 0 gives me my equation of motion. Okay, so now let me see what happens to my Polyakov action. Okay, I'll come back to my Polyakov action. Polyakov action once again. S is minus T by 2 into D2 sigma into, or let me take it inside, then this is X dot square minus X prime square. The guiding line to remember is that kinetic energy has to be positive. So this, if I have minus here, then I would have minus here plus here, but if I take it inside, this would be like that. Very good. So let us define those similar objects, pi mu, and I put the subscript tau. Earlier I had not put, but on purpose I want to put it now. So this I should write as L d2 sigma. So rest of the things you can identify, del L over del x mu dot, and this would be T by 2 times twice x dot ht x dot and pi mu sigma. Let me define x prime mu. This would be minus T by 2 or T by 2 into minus 2x prime mu. If it is mu here, this would be here, this would be here. This is equal to minus T x prime mu. Very good. And now let me take its time derivative once again, del tau of pi mu tau plus del sigma of pi mu sigma. Then this would give me T x double dot mu minus T x double dot mu, and this is my famous del tau square minus del sigma square x mu, and T is sitting here, and this I know is 0. Why? Because I can multiply it with minus 1 and minus 1, and this gives me equal to minus 1 times my x mu, and this I know, we have already known that this guy is 0. So this tells me that this guy is also 0. Okay, so I can write down the equation of motion for the Polyakov action also in this form, in which I wrote down the equation of motion for the Nambu-Goto action. In fact, this you could also write as, okay, I can take minus 1 common here, and this is del inversion of x mu to 0. So whether it's our equation of motion then remains equal to 0, and this is del inversion of x mu equals to 0, where this is nothing but del mu, not mu now, maybe lambda x mu, or I could write it as delta lambda. So I could write this equivalently in different forms, and that would be my equation of motion for this various the Polyakov action and the Nambu-Goto action, right? my watch says we could use another 5 minutes or so, and in that time, I could do a very simple, I could give you a very simple exercise, namely that for this, let me first write down the results and then we can quickly derive. So, I would speak on that at length later on, but we could simply mention the following, which we, you see, in quantum mechanics, what we do is we calculate the commutation relations of Q's and P's, right? What we do in field theory is we calculate these Poisson brackets or commutation relations at the equal time. So they are called equal time commutation relations. Okay, and then I would gradually introduce light front quantization, which is very helpful for solving the equations of motion for our string. And I mean, you can solve even in the other coordinates, which are called instant form coordinates. And this other one is called as the light front coordinates. Both of them are given by Mr. Paul Dirac, my most favorite physicist. He gave actually 3 different forms of dynamics: instant form, light front, and point form. But so far we have never used the point form dynamics, but we have used these 2 extensively, instant form and light front.